Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the starting point. Generate the full essay from it. Introduction. In the annals of computational theory, certain works stand as monumental bridges, connecting previously disparate realms of mathematics, physics, and computer science. Peter Shor's 2012 publication, Polynomial Time Algorithms for Prime Factorization and Discrete Logarithms on a Quantum Computer, undeniably occupies such a position. This seminal paper, though predated by earlier publications on the topic, offered a refined and accessible exposition of an algorithm poised to revolutionize cryptography by leveraging the counterintuitive principles of quantum mechanics. It posited a method by which a quantum computer, a machine harnessing superposition and entanglement, could efficiently solve problems considered intractable for classical computation, specifically prime factorization and discrete logarithms, upon which widespread encryption schemes crucially rely. This essay embarks on a critical evaluation of the claims within Shor's work. Through a detailed, section-by-section analysis, it will dissect his argumentation, scrutinize his methodology, and contextualize his conclusions within the broader landscape of quantum computing and cryptography. The objective is to provide a comprehensive assessment of the paper's validity, significance, and enduring impact, acknowledging both its groundbreaking contributions and the nuanced complexities inherent in its theoretical underpinnings. Section 1: Introduction and Overview of Quantum Computing. Shor begins by elucidating the fundamental tenets of quantum computation, contrasting them starkly with the deterministic nature of classical bits and logic gates. He introduces the concept of a quantum bit, or qubit, which, unlike its classical counterpart, can exist in a superposition of states, simultaneously representing 0 and 1 with associated probabilities. This, he asserts, grants quantum computers an inherent parallelism, capable of exploring a multitude of possibilities concurrently. He underscores the importance of quantum entanglement, a phenomenon where two or more qubits become correlated in such a way that the state of one instantaneously influences the state of the others, regardless of the distance separating them. Shor explicitly states that controlled quantum operations, analogous to classical logic gates, can manipulate these entangled qubits to perform computations unattainable by classical machines. He claims that quantum Fourier transform is a core algorithm enabling quantum computation to solve prime factorization and discrete logarithms, something that is classically unable to be efficiently achieved. The essay evaluates Shor's claim regarding the inherent parallelism of quantum computers arising from superposition. It is important to observe that this inherent parallelism is not a simple case of doing exponentially many classical computations in parallel. The key difference lies in the fact that measuring the final state of the quantum computation only reveals a single outcome. The challenge and the ingenious contribution of Shor's algorithm lies in designing quantum operations that steer the superposition towards states that, when measured, yield the desired solution with high probability. The argument concerning quantum entanglement is also crucial. While frequently cited as a defining characteristic of quantum computing, one must acknowledge that mere entanglement does not automatically equate to computational advantage. The entanglement must be carefully engineered and manipulated to facilitate the specific algorithmic steps required for the solution. Shor's work, to its credit, precisely details how this engineering is achieved within the context of factorization and discrete logarithms. Finally, the importance of the quantum Fourier transform is a pivotal element, enabling the algorithm to efficiently extract the periodicity of a function, which is an essential step in both factorization and discrete logarithm computations. The claim of classical intractability is appropriately emphasized, as it forms The fundamental justification for exploring quantum solutions, Section 2 Quantum Fourier Transform and Phase Estimation. Shor dedicates a significant portion of his paper to explaining the quantum Fourier transform, or QFD, and its application in phase estimation. He presents the mathematical formulation of the QFD, demonstrating how it transforms a quantum state representing a function's values into a new state representing its Fourier coefficients. He emphasizes that the QFD can be implemented efficiently on a quantum computer, requiring a number of quantum gates that grows polynomially with the number of qubits, a result contrasting sharply with the exponential complexity of the classical discrete Fourier transform. Shor then elaborates on phase estimation, a crucial subroutine that employs the QFD to accurately determine the phase of an eigenvector of a unitary operator. The essence of this process involves applying the unitary operator repeatedly, controlled by a series of qubits, and then using the QFD to extract the phase encoded in the resulting superposition. He posits that accurate phase estimation is pivotal in determining the period of a function, a necessary ingredient for both prime factorization and discrete logarithm computations. Examining Shor's claim regarding the efficiency of the QFD, it is vital to acknowledge the subtleties involved. While the quantum circuit implementing the QFD as polynomial gate complexity, the preparation of the input state and the measurement of the output state compose challenges. Specifically, preparing the appropriate superposition representing the function's values may require significant resources. Depending on the nature of the function itself, the phase estimation subroutine also warrants critical attention. The accuracy of the phase estimate depends directly on the number of qubits used to represent the phase. Obtaining a highly accurate estimate necessitates a correspondingly large number of qubits, which can impact the overall resource requirements of the algorithm. Furthermore, the probability of success in phase estimation is not always guaranteed, particularly when the phase is not a rational number with a small denominator. Shor's analysis accounts for these possibilities, and indeed provides the framework for determining the number of qubits needed to achieve a desired probability of success in finding the phase. The connection between phase estimation and period finding is presented clearly, establishing the essential link between the quantum subroutine and the target problems of factorization and discrete logarithms. Section 3. Prime factorization algorithm. Shor's paper provides a detailed explanation of how the quantum Fourier transform and phase estimation are employed to achieve prime factorization. He starts by outlining the number-theoretic underpinnings of the algorithm, highlighting the connection between finding the period of a modular exponentiation function and determining a non-trivial factor of the number to be factored. Specifically, he shows that, given a composite number n, if one can find an integer coprime to n and determine the period r of the function raised to the power of x modulo n, then, with a reasonably high probability, the greatest common divisor of a raised to the power of r divided by 2, plus 1 and n, will yield a non-trivial factor of n. Shor then describes how this period finding can be efficiently accomplished using a quantum computer. He outlines the steps involved in preparing the initial superposition, applying the modular exponentiation function as a controlled, unitary operator, performing the quantum Fourier transform, and measuring the resulting state to obtain an estimate of the period. He claims that by repeating this process multiple times, one can obtain a sufficiently accurate estimate of the period to successfully factor the number. Evaluating Shor's prime factorization algorithm, one must acknowledge its probabilistic nature. The algorithm does not guarantee to find a factor in every run. The success depends on several factors, including the choice of the random number A, the accuracy of the phase estimation, and the properties of the number being factored. The essay observes that the choice of A is crucial. If A is not coprime to n, the algorithm will fail. More generally, even if A is coprime to n, the period of R may be such that A raised to the power of r divided by 2 is congruent to -1 modulo n, in which case the algorithm also fails. Shor's analysis addresses these possibilities, demonstrating that if the algorithm is repeated a sufficient number of times with randomly chosen values of a, the probability of finding a factor becomes arbitrarily high. It is also important to note that the classical pre- and post-processing steps in Shor's algorithm, such as checking for trivial factors and computing the greatest common divisor, contribute to the overall complexity. While these steps are polynomial in the size of the input, their computational cost cannot be entirely ignored. An irony exists in this dependence on classical algorithms for preparing the quantum inputs and interpreting the quantum outputs, highlighting the synergistic interplay between quantum and classical computation. The claim of polynomial time complexity, therefore, pertains to the quantum portion of the algorithm, which is the performance bottle. Section 4. Discrete logarithm algorithm. Following the presentation of the prime factorization algorithm, Shor extends his quantum approach to solve the discrete logarithm problem. This problem, considered intractable classically for large numbers, is fundamental to many cryptographic systems. Shor presents the mathematical formulation of the discrete logarithm problem given a group G, a generator G of the group, and an element H in the group. Find the integer x such that g raised to the power of x equals h. Shor demonstrates that this problem can be recast as a period-finding problem, similar to the factorization case. He defines a function whose periodicity is directly related to the discrete logarithm, and then shows how the quantum Fourier transform and phase estimation can be used to efficiently determine this period. Shor outlines the steps involved in preparing the appropriate superposition, applying a unitary operator representing the group operation, performing the quantum Fourier transform, and measuring the resulting state to obtain an estimate of the period. He asserts that with a high probability, the discrete logarithm can be extracted efficiently from this period estimate. Evaluating Shor's discrete logarithm algorithm, it is important to appreciate its generality. Unlike the factorization algorithm, which is specific to integers, the discrete logarithm algorithm applies to a wider range of finite groups. This generality makes it a potentially powerful tool for attacking a variety of cryptographic systems that rely on the hardness of the discrete logarithm problem in different groups, such as elliptic curve cryptography. The essay observes that the efficiency of the discrete logarithm algorithm depends on the efficient implementation of the group operation on a quantum computer. For some groups, such as the multiplicative group of a finite field, the group operation can be implemented relatively easily. However, for other groups, such as elliptic curve groups, the implementation of the group operation can be more complex and may require significant quantum resources. The success of the algorithm also depends on the choice of the group G and the elements G and H. If the group is too small, the discrete logarithm problem can be solved easily using classical methods. However, if the group is too large, the quantum computation may become intractable, even with Shor's algorithm. Shor's analysis provides the framework for understanding these trade-offs, allowing one to estimate the quantum resources required to solve the discrete logarithm problem in different groups. Section 5. Resource requirements and scalability. Shor addresses the crucial question of resource requirements and scalability in his paper. He outlines estimates for the number of qubits and quantum gates needed to implement his algorithms for factoring numbers and computing discrete logarithms of practical cryptographic sizes. While precise figures depend on specific implementation details and advances in quantum hardware, Shor provides a general framework for assessing the feasibility of quantum attacks on current cryptographic systems. He acknowledges the significant technological challenges involved in building large-scale, fault-tolerant quantum computers, but argues that continued progress in quantum computing research makes the development of such machines a plausible scenario in the foreseeable future. Shor makes claims about how future machines will be able to scale to meet the challenges of modern encryption. Critically evaluating Shor's assessment of resource requirements, it is essential to acknowledge that his estimates were based on the state of quantum computing technology at the time of publication. Since then, significant progress has been made in both quantum hardware and quantum algorithms. For example, improved quantum error correction codes have been developed, which can reduce the number of physical qubits required to implement a logical qubit. Furthermore, researchers have devised optimized quantum circuits for modular exponentiation and the quantum Fourier transform, which can reduce the number of quantum gates needed for the algorithms. However, despite these advances, the construction of a quantum computer capable of factoring realistically sized RSA keys or solving discrete logarithms in elliptic curve groups remains a formidable challenge. The essay observes that the primary obstacle is the need for a large number of qubits with high fidelity and long coherence times. To coherence, the loss of quantum information due to interactions with the environment is a major hurdle that must be overcome to build fault-tolerant quantum computers. The scalability of quantum computing technologies is also a significant concern. While small quantum computers with a few tens of qubits have been built, scaling these systems to thousands or millions of qubits presents enormous engineering challenges. Shor's claims regarding future scalability must be viewed in light of these ongoing challenges. Section 6. Impact on cryptography and security. Shor explicitly addresses the profound impact of his algorithms on cryptography and security. He emphasizes that the existence of efficient quantum algorithms for factoring and discrete logarithms poses a severe threat to widely used public key cryptosystems such as RSA, Diffie-Hellman, and elliptic curve cryptography. These systems rely on the computational intractability of these problems for their security. If a sufficiently large quantum computer would be built, it could break these cryptosystems relatively easily, compromising the confidentiality and integrity of sensitive data transmitted over the Internet and stored electronically. Shor advocates for the development and deployment of post-quantum cryptography. Cryptographic algorithms are believed to be resistant to attacks by both classical and quantum computers. He claims that these algorithms are essential to ensure the long-term security of digital communications in a world where quantum computers may become a reality. Evaluating Shor's assessment of the impact on cryptography, it is important to recognize that the threat to current cryptographic systems is not merely theoretical. The possibility of a quantum computer being built at some point in the future is a real concern that motivates the need for proactive measures. The essay observes that the transition to post-quantum cryptography is a complex and multifaceted undertaking. It involves the development of new cryptographic algorithms, the standardization of these algorithms, and the deployment of these algorithms in real-world systems. This process requires the coordinated efforts of cryptographers, computer scientists, engineers, and policymakers. Furthermore, it is important to note that there is no guarantee that all post-quantum cryptographic algorithms will remain secure forever. As quantum computers become more powerful, new quantum algorithms may be developed that can break even these algorithms. Therefore, it is essential to maintain a continuous effort to monitor the progress of quantum computing and to develop new cryptographic algorithms that can withstand future quantum attacks. The urgency of this situation is occasionally met with skepticism, a curious paradox given the potential ramifications. Section 7. Reception and subsequent developments. Shor delves into the reception that was afforded upon his paper and some of the advances that have come since it was published. He discusses the initial skepticism that greeted his results, particularly from those who doubted the feasibility of building large-scale quantum computers. However, as progress in quantum computing research has continued, the acceptance of his work has steadily grown. Shor also highlights some of the subsequent developments that have built upon his original ideas. These include improvements to the quantum algorithms themselves, as well as the development of new quantum error correction codes and quantum hardware architectures. He claims that through new technologies, quantum computing continues to grow exponentially. In critically evaluating the reception and developments related to Shor's work, it is important to acknowledge the wide-ranging impact on the field. While the initial skepticism was understandable due to the technological changes involved, Shor's paper catalyzed a tremendous amount of research in both quantum computing and post-quantum cryptography. The essay observes that his algorithms have served as a benchmark for assessing the capabilities of quantum computers. Researchers have used Shor's algorithms to estimate the resources required to break various cryptographic systems, and these estimates have guided the development of new post-quantum cryptographic algorithms. Furthermore, Shor's work has inspired the development of new quantum algorithms for other problems, such as quantum simulation and quantum optimization. The ongoing progress in quantum computing research is a testament to the enduring influence of Shor's pioneering work. The transition from theoretical algorithms to experimental demonstrations is a slow process. The underlying principles remain as relevant as ever. Section 8: Potential Limitations and Future Research. Shor reflects on the potential limitations of his algorithms and suggests directions for future research. He acknowledges that his algorithms are not a panacea for all computational problems. He emphasizes that they are specifically tailored to problems with certain mathematical structures, such as factorization and discrete logarithms. He speculates that the development of new quantum algorithms that can solve a wide range of problems remains a significant challenge. Shor also identifies the need for further research in quantum error correction and fault-tolerant quantum computing. He claims that, without a fault-tolerant quantum computer scale, in critically evaluating the limitations and future research directions identified by Shor, it is important to recognize that his algorithms represent only one aspect of the broader field of quantum computing. The essay observes that, while his algorithms have had a profound impact on cryptography, they are not necessarily applicable to all computational problems. There are many problems for which classical algorithms are still more efficient than known quantum algorithms. Furthermore, the development of new quantum algorithms is a challenging task that requires a deep understanding of both quantum mechanics and computer science. The need for fault tolerance in quantum computing is a fundamental limitation that must be addressed before large-scale quantum computers can be built. Quantum error correction is a promising approach, but it requires significant overhead in terms of qubits and quantum gates. Therefore, the development of more efficient quantum error correction codes is an essential area of future research. Section 9: Broader Implications and Philosophical Considerations. Shor broadens the scope of his discussion to consider the broader implications and philosophical considerations surrounding quantum computing. He reflects on the potential societal impacts of quantum computers, both positive and negative. He acknowledges that quantum computers could be used to solve important scientific and engineering problems, such as drug discovery and materials design. However, he also cautions that they could be used for malicious purposes, such as breaking cryptographic systems and developing new weapons. Shor emphasizes the importance of ethical considerations in the development and deployment of quantum computers. He claims that collaboration is necessary between scientists, policymakers, and the public to ensure that quantum computers are used for the benefit of humanity. In critically evaluating the broader implications and philosophical considerations raised by Shor, it is important to recognize that quantum computing is not merely a technological development. It is a scientific revolution that has the potential to transform society in profound ways. The essay observes that the ethical implications of quantum computing are particularly important. As quantum computers become more powerful, it is essential to consider the potential consequences of their use and to develop safeguards to prevent them from being used for harmful purposes. The need for collaboration between scientists, policymakers, and the public is crucial to ensure that quantum computing is developed and deployed in a responsible and ethical manner. The philosophical ramifications extend beyond mere practical considerations. They challenge fundamental assumptions about the nature of computation and the limits of knowledge. Conclusion: Peter Shor's 2012 work, Polynomial Time Algorithms for Prime Factorization and Discrete Logarithms on a Quantum Computer, remains a watershed moment in the history of computer science. His presentation of efficient quantum algorithms for factoring and discrete logarithms not only demonstrated the potential power of quantum computation, but also revealed a fundamental vulnerability in widely used cryptographic systems. Through careful section-by-section analysis, this essay has scrutinized the claims and arguments presented within Shor's paper, highlighting both its groundbreaking contributions and the nuanced complexities inherent in its theoretical underpinnings. While the practical realization of larger-scale quantum computers capable of breaking current cryptosystems remains a formidable challenge, Shor's work has catalyzed a tremendous amount of research in both quantum computing and post-quantum cryptography. His algorithms have served as a benchmark for assessing the capabilities of quantum computers, and his ideas have inspired the development of new quantum algorithms for other problems. The enduring significance of Shor's work lies not only in its technical brilliance, but also in its profound implications for cryptography, security, and the future of computation itself. The continued exploration of these implications is essential to ensure that quantum computing is developed and deployed in a responsible and ethical manner, safeguarding the security and privacy of digital communications in an increasingly interconnected world. His paper has set the stage for the next leap in computing technology, something that is unlikely to slow any time soon.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.